Okay.
Great, thank you.
All right, lovely. Okay, so we talked that I will begin the presentation and then Paul will take over. Does that sound good to the people in the room? Is it good enough to hear?
Yes.
Yes. Okay, great, great. Okay, so hi, hello. So I will, first talk a little bit about the work that the behavioral metrics group did. So we were led by Barbara and TA'd by Sebastian and Paul, and there were 5 students in our group. So there was Avi, Carrie, me, Martina, and Wojtek. And we will especially go into the idea of compositionality of a particular lifting called the Kantorovich lifting, and mention also an application in up-to techniques, which we focused a little bit on in the research week and are definitely eager to go forward with in the future as well. So that's a future research direction as well. Yeah, so at first, yes, the slides, yeah, okay, they say change now. So the table of contents. So at first we will just introduce the topic of behavioral metrics briefly, and mention a few different kinds of coalgebras which are relevant in this discussion. And then we will really dive into more the mathematical gears that you need to get, like quantiles and what categories we're working in. And then I will define the Kantorovich lifting, and then after that, Paul will dive into what compositionality exactly means, what results we have, and also how we can use it to lift natural transformations and why that might be important. Yeah. So for the introduction, so the reason we care about lifting functors into, so usually we have functors on set, and then we want to lift them into some category that has a forgetful functor into set. But the motivation for that is that there is this idea of coalgebras for endofunctors. And they are used in different ways to model transition systems of various kinds. So for example, to model deterministic finite automata, Kripke frames, label transition systems, probabilistic transition systems. And what they have in common is that they can all be modeled as these functions from a set X into the image of that set X under a specific functor. So for deterministic finite automata, that functor, for example, would take X to the product of the 2-element set and all the functions from and given alphabet A into X. And now something that is also well studied in the field of coalgebra is behavioral equivalence. And that means that in broad strokes, the automata or transition systems, they behave the same way. And that can be modeled using final coalgebra, which we're not really getting into, but it kind of yields these different notions of equivalence for different transition systems. And it's robust and it works, but it's maybe a little bit rigid at times. But yeah, so the coalgebra definition is that if we have an endofunctor f from C to C, then a coalgebra is just an arrow in that category from X to Fx. And now equivalence is definitely very useful, but sometimes, especially with maybe in certain more quantitative settings, it might be more useful to consider behavioral distance. So here we have this this automaton in the probabilistic setting. So we have a probabilistic transition system. And if you look at the states X and Y, then X, so Y, let's start with Y, actually, that's a simpler one. So Y has the probability, half probability to go into U and half probability to go into V. And whereas X has almost, for some sort of given epsilon, almost the same probability to go into U and V, especially if epsilon is small. Well, if epsilon is large, then that doesn't really hold. But given that it's very small, then we might want to express that these two states are actually similar, even though they're not the same. And if epsilon gets really small, then it might be, we might want to have some ways of quantifying that. So that is really the motivation of the behavioral distance. And looking at the other two states which we haven't mentioned, so U and V, For example, we can see that V doesn't have any arrows going out of it. So V is a trap state, and it's modeled by the one in the signature of the transition system. And so we may want to say that a trap state and a non-trap state are completely different. So they're maximally different. So here they would have the distance 1, if we say 1 is the maximum distance. So there are various things to express about these systems with distance. And now, if we have a lifting, which is given by this commutative diagram with forgetful functors, then we can also find the behavioral distance. Now first, a lifting means that if we have a functor on set, and we go into the category, well, here we have taken pseudometric spaces. So pseudometric spaces, the objects are pseudometric spaces, and the morphisms between them we have taken to be non-expansive maps. They work well for this work, but they're not the only choice. But here, if we lift a functor on set to pseudometric spaces, it means that for every pseudometric space x, d, we give a new pseudometric space fx with a new pseudometric, and that new pseudometric is really the way you define it gives an important part of the lifting. And we can use this new distance that we defined on fx to find the behavioral distance between two states. And how we do that is that we define behavioral distance as the greatest fixed point of a function. And that function takes a pseudometric on x and gives a new pseudometric on x using the lifted metric on fx. So it precomposes that metric on fx with the Coalgebra function. And doing so and finding the greatest fixed point of that function gives us actually the behavioral distance. And now, for example, if we want to look at a quick example here, then here we have this coalgebra, which is a deterministic automaton with now not a two-element set as it's which indicates whether it is an accepting or a accepting or state or not, but we have a continuous unit interval that expresses a fuzzy measure of how accepting a state can be. And now the induced metric, if we start out with some sort of a metric on the space, then the induced metric gives us the maximum between the fuzzy expression of acceptingness and the distance of A successors and distance of B successors. And now, if we take the first metric to just be the zero metric, which makes our job a little bit easier, then at first we get that the distance between x and y is 0.2, because we see that the only non-zero element in the maximum, the set over which we find the maximum is 0.5 minus 0.3. So at first we get 0.2 over there, then we get the distance between y and z to be 0.5 and between x and z to be 0.7. But now if we look at the distance between x and y, what we get is that doesn't actually remain at 0.2, because on the second step, we take, again, we have the maximum over the difference, 0.5 minus 0.3, which is still 0.2. But now we take the previous distance that we obtained on the A successors and the B successors. And now we see that with the A successors, we get the distance d of y and z, which we got in the previous step, that it is 0.5. And similarly, if we take the B successors, then we get the distance of z and y, which is also 0.5. So in fact, we see that at depth 2, the distance between x and y changes. And so that's how and then if we find the fixed point of this process, then that gives us the behavioral distance between two states. So maybe that illustrated a little bit of how this process works. Yeah, so now I will go on to quantals and what categories we're really looking at. And so for that, first we have a quantal V, which is, so first we should define a quantile. So that's a complete lattice with an associative operation, and it distributes on both sides over arbitrary joins. And now if this operation has a unit, then that unit is denoted by 1. And it turns out that we can actually use this associative operation to also define a distance function on the quantile, and that is very handy for us. Some examples of quantiles are, for example, the two-element set with the associative operation being and, I believe, and also the unit interval with truncated addition. And now we are going to look at quantile valued predicates and quantile valued relations. And that just gives us that, those just mean maps from X to V and maps from X cross X to V. And now these, we take quite a loose sense of relation, but actually we're going to make it more rigid in a second, and we're going to impose reflexivity and transitivity, which will make it look more like a metric. But first we just consider relations. And now building on these predicates and predicates and relations, we have the categories vpred, which is the category with objects being the predicates, so maps from X to V, and morphisms are maps from maps F from X to Y, such that P is less than Q composed with F. And now VSPred is quite similar, except now the objects are not single predicates, but subsets of predicates from X to V. And now we define the maps to be functions f x to y, such that when we pull back the predicates along f, so we mean that we compose Q and F, just like we did in the predicate situation, then we have that Q composed with X is also in S. And then the third category that is really relevant for us is VCAT, and that is a category of relations on X to V, and relations in particular that are reflexive and transitive. So reflexivity in particular means that the distance from an element into itself is greater than 1 for all X. And transitivity means that bulleted D is less than D. So in particular, these conditions they emulate this idea of if you have a hemimetrics, then there is this concept that it should have dxx is 0, so a distance from an element to itself should be 0. And then transitivity in a quantile way is the triangle inequality. So it reflects that. And that's, so VCAT actually gives us the category of hemimetric spaces. And then if we also add symmetry, which is that the distance dxy is the same as dyx, then we get the category of pseudometric spaces. This is very embarrassing, but I need to charge my laptop. So I will just do that in a second, and I will be back. Pardon.
Okay. Yeah, so probably I will just take over then. But then, so Johanna,
I'm actually back if you go.
Yeah, so Johanna, we're actually kind of short on time. Maybe you can just stop the screen share and I can start mine.
Okay.
Just go a bit over the remaining slides in whatever time we have left. Share screen. Relevant, I guess. The remaining slides in whatever time we have left. Share screen. Relevant, I guess. So, okay, so this is actually going to be a bit tough to do in the remaining time, but let's see. Okay, anyway, so we have these v-valued predicates, and we also have this notion of v-valued categories. And as Johanna was saying, that these are essentially a generalization of metric spaces. And so one thing that exists between these two categories, so this one category of metric spaces and this category of sets of predicates of these, is an adjunction. And this adjunction comes in two parts. So if you have a set of predicates, then from these you can actually compute a distance, which just arises by evaluating all these predicates and taking the maximum distance that you get. But because we're in quantals, the maximum distance actually turns into an infimum. And then conversely, if you have a distance, then you can extract from this distance the set of non-expansive maps, or V functors in quantalic parlance. And so one thing that we worked out during the week was that these two actually form a fibered adjunction, so not just an adjunction, but one that actually represents, works well with the underlying structure of sets. Okay, and then I guess I'll do the control ridge lifting and then still say what compositionality for that means and skip the rest. So the thing is, if we have a so-called predicate lifting, where's that slide? Oh, there's that slide. So a predicate lifting is something that turns a predicate on some set X into a predicate on some set Fx. And one simple example of that would be this second one here, where say we have some predicate that is valued in the unit interval. And we want to turn this into a predicate on the set of probability distributions. And one way of doing that is just, well, this thing P can be thought of as a random variable, so we can take its expected value. And taking this expected value actually turns out to be such a predicate lifting. And now, if you have a predicate lifting, or actually a set of these predicate liftings, then this gives you a map from sets of predicates to sets of predicates, where we just take all the predicates, take all the predicate liftings, and combine all of these. So this one should also include some set comprehension over elements, small lambda of large lambda. And the idea behind the control ridge lifting is that if we have this map on the category of sets of predicates, then using this adjunction, we can turn this into a map on the V categories. And this is highly abstract, but it turns out that if you instantiate this just right, actually using this expected value modality, then what you get is the original control ridge construction from, I think, the 1940s, which was motivated by transportation theory. But now we do this in this highly general way. And so the question that we concerned ourselves with during the week was that of compositionality, which is essentially, oftentimes we consider coalgebras of composed functors, so functors that are actually the composition of two individual functors. And if you want to lift these, then ideally what you want to do is lift the two functors individually and then compose these liftings with one another. And the question is really, so if you do this, does this sort of lifting agree with the composition of predicate liftings? And yeah, we did a lot of work on that. We got a few negative results. We got a few positive results that are actually a bit brute force-ish and where you need lots of these predicate liftings. So we did some work to improve these. Yeah, the up-to techniques I will not talk about very much. So here's a few of the results that we got. So we got some negative examples where compositionality fails. We got some conditions under which compositionality holds. As I mentioned, this is the first point. We established this fibered adjunction. Then we also proved some generic version of the so-called McShane-Whitney extension theorem, which is basically something about this V as spread. Right. We have a few pictures. Those were nice. So we worked in groups of 2 and 3, and we found that to be working quite well. And we also have still a bunch of homework to do if we actually want to eventually make a publication out of this, but we're decently confident. All right.
Paul and Johanna, this group was mentored by Barbara Koenig. Okay, I don't know, does anyone have a really quick question they want to ask? If not, Paul.